by kind of adjoining objects of parameters to the domains, or kind of dually the codomains of the morphisms in the category we started with. And this is important in cybernetics because we can think of these parameters as representing some data, say, about the world that needs to be learned, some, say, information about the structure of the external environment, or something like that. And it's also important in the context of optics because they are the things that go, say, you've seen this kind of thing before. C, A, M, tensor, B. This is the kind of Hom set in a category of optics, M, tensor, D, E, something like this. But this kind of tensoring on the domain or the codomain is kind of the same thing as the power construction. And so there's a kind of deep connection between optics and potentially their generalization into dependent optics, which I know people, say, at Stratified and elsewhere are working on, and this power construction. But for me, I've got three particular motivations for giving this kind of talk. And this is because this same kind of idea shows up quite a lot in the kinds of structures that I've been working with, particularly to do with Bayesian inference and that kind of sort of random cybernetics, or cybernetics in a kind of stochastic environment. And that's really often because the kind of randomness in these circumstances, in these situations, can often be thought of as coming in as kind of some kind of parameter. Often these things called generative models are kind of really written as, say, some kind of deterministic map, which is parameterized, and a distribution on the parameter space. And we think of that parameter space or that distribution as kind of representing the noise source of our model. But the trouble is there's kind of not enough objects, in a way that I'll explain, in these para categories, in these parameterized categories, as they're kind of standardly introduced or talked about. And so we can't really do things that we might want to do, like form limits in, say, power of C, or really talk about things like types in a satisfactory way, in particular dependent types. And occasionally I found that it's quite interesting or can be quite useful to sort of think about generative models or sort of stochastic processes of this kind, often as kind of having a kind of dependent type-like structure, but there's no real way to say that precisely. And so often I've been kind of seeking something that we might think of as Bayesian dependent optics to kind of go into this, this kind of slightly unknown world of dependent optics that people have been trying to investigate right now. And that I think that world of dependent optics is also, pertinently for this series of talks, the thing that might be at the intersection of, say, polynomial functors and the optics stuff we've heard about already. And so I've been thinking about how to talk about parameterized categories, or categories where the morphisms have got parameters, in a way in which we'll be able to use kind of type theoretic thinking. And that's the thing that underlies the kind of the three main motivations that I'm going to talk about in a moment. The three motivations I've given here for this structure that I've been calling categories by proxy. Now, I am aware, and unfortunately I've used this phrase before in a kind of slightly different context of enriched categories. The context I'll be talking about today is of internal categories, and I think this is probably the proper way to do the construction that I'll be describing. And so I hope people will forgive me for sort of overloading the sort of vocabulary in this way. I don't think categories by proxy has really caught on yet, if it ever does. And so I think it's okay to sort of redefine it in the way that I'm slightly more satisfied with. Okay, but sort of without further ado on introduction, I'll just summarize these motivations. The first one is that these generative models, the things that I'll be making precise shortly, are kind of really like, when we think sort of type theoretically, they're really like terms of random types, or sort of random terms of types, or something like that. The second motivation, as I mentioned, is that these parameterized categories, para of C for some monoidal categories theory C, they don't really have enough limits. And this means they don't really have the kind of rich internal language we might like. And then finally, as I mentioned, I'm really seeking this notion of Bayesian-dependent optics. And that would be something that generalizes Bayesian lenses to a kind of dependently typed setting. So we'll start with number one. So what do I mean by generative model? A generative model is something that in kind of various scientific fields can be thought of as generating predictions, whatever that might mean, of observed data from beliefs about, say, causal or latent states. And really, okay, that sounds fancy, but it's actually quite a simple thing, quite a simple idea. It's a pair of two things, something pi and something c, where pi is a state, and I've written the dot on the arrow here to say that this is a kind of arrow in a Markov category or a copy-delete category, like the equalizer category of some probability monad. And so this pi is a state or a probability distribution on X, and C is what's known as, or often what's known as a Markov kernel or a stochastic channel. In this equalizer category, of course, that's this type X to dy, and so it says, given some element of X, I give you a distribution over Y, and so we could think of this Y as being the space of observed data, and this X as being the space of latent states or kind of structures from which we will sort of generate these predictions. They could be a sort of kind of summaries of the observed data or kind of beliefs about causal structures or something like that. And because these copy-delete categories come with a nice string diagram calculus, these things are often drawn in this kind of way, where you've got this pi. We write pi often because we think of it as, say, a prior, to use the kind of term that comes up in say, statistics and machine learning. And this is, say, some joint model, some joint distribution then on X and Y. So it's something that says, okay, well, I've got beliefs over our causal or latent states and beliefs about over our observed data, and these things might be correlated, of course. Now, there's something funny about this, which is that if C is deterministic, so really it's just something like X to Y in set, say, and pi is a Dirac distribution, so all of its probability is concentrated on a single point. That is, it just assigns probability 1 to that point. Then, of course, we can interpret this diagram in set, and we can really think of this, the top part here, this part, as representing just the graph of this function C, which is going from X to Y, of course. And then, we can discard this Y leg because we've got this nice deleting structure in set and in these copy-delete categories. And they have to satisfy this rule that if we just discard this thing, because 1 is terminal in set and C is deterministic, it's the same as not doing anything at all. It's the same as, oh no, my screen has died. Excuse me, sorry. Oh no, sorry, hold on. I may have to restart this thing.
I do see your screen now.
I know, but unfortunately the slide is stuck, annoyingly. I will just bring it back. So the thing I'm saying is that, okay, I can talk through this slide with my mouse. This gets going again. So yes, we can throw away this Y leg and we just get X again. So this just is the sort of comoid law. I mean, and using the fact that 1 is terminal in set, this is all just saying that this thing here, which I call the graph of C, is a section of this trivial bundle, this product of X and Y, and this map the projection from X times Y back down into X. And then, of course, pi being a sort of Dirac distribution, it just corresponds to an element of X. And it's this kind of thinking that sort of justifies slightly more formally this thing I said earlier about thinking of these generative models as like stochastic or random terms, because of course sections of bundles, so general morphisms, say like this, E to B, are in type theory, they're the semantics for terms of E in the context of B. I think I'll be able to get my slides up shortly again. And so, where are we going? And so it's sort of, if we forget the randomness for now, and this is the thing I want to sort of be able to put back in, generative models are really like terms equipped with a belief about this context object. Okay, let's see about this. And this is the thing I want to make precise. So that's our sort of first piece of motivation. Let's see now. Okay, great, that's back. So, okay, then as I mentioned at the beginning, the randomness in a generative model often comes from a parameter. So, you know, we've got this C map X to distributions on Y. Then really, in a lot of situations, particularly in science, these are kind of deterministic maps X times omega for some noise space omega into Y. And we've sort of brought this along with some distribution on omega to really make it act like a noise space. And we sort of, if we can sort of push this noise forwards through the map to get this channel X to dy. And the way this works is like this. We say, okay, well, I can just take my X. I say, oh, I've used the unit of this monad structure on D, gives me a dx. It's just the thing that gives me these direct distributions. I can use the commutativity of the monad structure on D with the product to get a distribution on X and omega, and then I can just push this noise forward, as I mentioned, through the C prime map to get a distribution on Y. And in many scientific papers, this is written as, okay, C prime of some point X plus some omega W, where they say this omega, where they say this omega is distributed according to some distribution alpha. And then, okay, in this case, each of these maps C prime of something given some point omega is really a term. It's, just a deterministic map X to Y. And we might want to reason about all of these maps, or rather about all of C accordingly. And then, this means that we need to use this internal language in order to be able to make use of this kind of type theoretic kind of reasoning. But the trouble is, para of C generally doesn't have enough objects. And so, okay, let's see what I mean by this. So what does this mean? What is this para category more precisely? As I mentioned earlier, the objects of this category, say C is set. The objects of para of set, like this, are set. So it's just the same objects as we started with in C. And then the arrows X to Y are triples, say, of a parameter space in set, and these maps, these sort of parameterized maps X, which I wrote as C prime before. Now there's a version of this where we can actually equip the parameter spaces with distributions as well, and then we get these maps where the kind of noise comes with them. And this, there's a version, we can show that this embeds into the Kleisler category nicely, but that's not important. This kind of noisy bit isn't really important for this slide right now. We might come back to it later. The trouble is that there aren't enough objects. So if we define this a little more precisely, we need to say, okay, what's the composition? Okay, the Helm sets of these things, a choice of parameter set and maps of omega times X into Y. And then given some F with the parameter omega from X to Y and some G with a different parameter gamma from Y to Z, we want to form their composite. It will have the parameter omega times gamma, which of course is isomorphic to gamma times omega. So how does this work? Well, we just sort of adjoin, first of all, this gamma object to the F map. So we've got gamma times F. This gives us gamma times Y. And then we can use G after that. So this is a composite, and we can show that this is associative unital, and it makes a category. And generally speaking, if we've got a symmetric monoidal category C, we can do the same kind of thing. But set is a topos. It's got all this really nice structure that we often like. And then the trouble is that power of set isn't even finitely complete. So we might ask, okay, we can define a product, that's okay, but we might want to do something more interesting. We want to think about equalizers. And so we ask, okay, what's the equalizer of two parameterized maps? They might have different parameters, or even the same parameter. So say they're both maps from X to Y with parameter P. Let's just draw that down here. It's going to be something like X to Y. We've got some kind of P things coming in here. This is F prime, and we want to form their equalizer. Well, we write out P times X to Y, and so for each, this is isomorphic to some map P to maps X to Y, which is to say that for each element of this parameter object P, we get a map F sharp of P from X to Y. And so if we want to form their equalizer for each choice of parameter, we'll have a different equalizer, because in general, this map F sharp of P is going to be a different map. And so really, we want this equalizer object to sort of be parameterized too. It needs to know what choices of parameter P are being applied to F and F prime in order to say what the equalizer is going to be. And so we might write this as something like equalizer P and P prime, but obviously this isn't an object. In particular, it's not. But there's no notion here of sort of parameterized object. And so this is what I mean by power of C not having enough objects to have a kind of satisfactory internal language. So we won't be able to talk about intersections or things like this. We can't do exponentials. There's a lot of structure that's missing.
Okay, so ask a question about para and its relationship to the Kleisli category. So suppose I'm very familiar with the Kleisli category itself. What you're doing for para is you're sort of giving, you're looking at morphisms inside the Kleisli category with additional structure, but there's like a natural functor from para back to the Kleisli category, right? That you gave on the previous slide that basically says, oh, you just compose, like if you take that data, you can actually construct a morphism in the Kleisli category. So is it just like giving more structure to the Kleisli category in some sense?
So are you talking about this part here?
Maybe I thought it was the previous slide where you decompose. Yeah, you're right here. Like you decompose your original morphism in the Kleisli category into some stuff, and I just don't know where this is coming from. Like maybe some intuition for why one would do this. Are we trying to like simplify computations because we're looking at like special kinds of parameter spaces, and then we could do calculus? Or why would one consider why would one consider this?
So I'm not going to say in general that every single map, say from X to dy, is of this form, although I believe it is the case in the finitely supported probability case. If you want a reference, if you read Tobias Fritz's paper, I think it's from 2019 on synthetic probability theory in Markov categories. I think that's where he gave the probability theory in Markov category. This is where he gave the definition, I think, of Markov category. There he talks about a notion called randomness pushback, where you can take any map X to in X to dy to a map of this form. Where you take omega to be the space of like maps X into Y using the internal Helm structure, say in sets, and then you can form some distribution on this exponential object. But I don't want to say that you can always do this for, say, measurable spaces. And so my motivation really for this is just that this is often something that people do in scientific papers when they want to give, say, a model of some stochastic process. That is, they say that there is some deterministic function that they know, and there's also some noise added to it. And so really all they're doing is saying they've got a deterministic function and they've got some noise source, and they're kind of doing something to make kind of make this deterministic function noisy. Here it's just adding the noise. And so, I mean, and you can indeed make a kind of para-like category. You can define, so this para is really often written for a monoidal action. So this is some monoidal action from some monoidal category C, M onto C. And you could define a kind of para category where the kind of morphisms are like P with this action on A and B. And so what we can do is we can define a category where the objects are, say, sets, and then sort of distributions on them. And we can, it's happening again. Sorry. And we can define a para category of that kind. But the thing is, I think that's kind of not the key point I was trying to make just then. All I was trying to say is that even in the case where you're just having set acting on itself, you don't get sufficient number of objects. Okay, let's see if this can return. I'm sorry, does that help answer your question? Well,
yes, I think so. Thank you.
Okay, great. Thanks.
I guess this might also be a good time for the question which I asked in the chat to save for later, and Matteo probably answered, which is how this relates to the quote unquote traditional para construction, which is a whole year old now, which doesn't have the distributions. So
yes, so that's precisely, yeah.
Yeah.
So that's precisely what I'm saying. We don't need, so even in that case, we don't have a kind of enough objects, as it were. I might just want to care about set acting on itself. I might want to talk about limits, or say equalizers in this para of set, and that's not a sensible notion because I don't have parameterized objects. And so the thing I'll eventually get onto is to say, give a way of giving these parameterized objects.
Yeah. Okay, so, but we don't. Are we right that we don't have to worry that, oh no, Toby's come up with a different para construction and now we've got two to worry about, because you have something like you have a category of states like the coastline unit.
So this, yes, exactly. So that's what's going on here, this coastline thing. But we can, I don't know how, yes, so we will see this in a minute. I want to sort of get on to the actual construction. Okay, and as I mentioned, there's this Bayesian dependent optics thing, which I guess at this point, given my technical problems, I might not have time to get onto. But I'll kind of skip past this and sort of move on. So before we get on to the new construction, there's a slightly different. Oh no, this is the para thing I mentioned already, where we've got a monoidal category. It should probably say symmetric. This is just the same thing I wrote on the previous slide for a monoidal category. Instead of having set with its product structure. And this is the thing I mentioned a moment ago, where para can be generalized. So where we've got this kind of monoidal action of some monoidal category on C. I want to note this just because the machinery I've been developing, hopefully it kind of gives us an internal category analog of this thing, except I don't really know entirely how the kind of more general version of the story goes, and it might be nice to talk about later. But before we get on to that internal category version of the story, I want to sort of reframe this para category in a kind of vibrational way, under the assumption that each object of C is equipped with a canonical comonoid structure, and certainly in the case of these copy-delete categories, these Markov categories, or even just sets, this is the case. So that's okay for my setting. Okay, so we can define this index category, which of course by the Grothendieck construction gives us this vibration, face down onto C. So how does it work? It's going to be sort of a pseudo functor from the opposite of C into cat, and it takes each object P to a category I've written power of P, whose objects are again the same objects as those of C, but whose morphisms are all of the form P tensor X to Y for some objects X and Y. And so now, rather than having two different parameters, say if we've got X to Y, Y to Z, we have on both the same parameter, and we can just sort of copy P into these two places because we've got this canonical comono structure. And so this is how composition works. We copy the parameter, and then we apply the parameter once for F, and then a second time for G. And then the identity is given just by throwing away the parameter object. This is indeed functorial because it acts on morphisms by precomposition along the parameter. So I sort of pull back. If I've got some map, say phi from Q to P, I can get a functor from power of P to power of Q by just precomposing phi on the parameter. It's just the same thing as this reparameterization thing you might have seen elsewhere. It's just sort of pulling back between the fibers. But there's still this problem in each fiber that we don't have enough objects to have limits. And so the idea that I've got is to add them in by considering generalized elements of C0, where C0 is this object of objects. And I consider these generalized elements to be the things that I'm going to call proxies. And so I'm going to have these generalized elements of objects and generalized elements of morphisms. But to say precisely what that means, I need to have this object of objects. I need to have another object of morphisms. And the kind of best setting, I think, to talk about that kind of thing is to think of C, rather than just as some category floating out there, to be an internal category in some other category, which I'll call its universe, and I'll write that as E. So just to make a little bit of notation precise, what does it mean to be for C to be an internal category in this way? Well, I've got this object C0 of C objects. That's an object in E. And again, I've got an object C1 in E, which is the object of C morphisms. And then I've got two morphisms in E from C1 to C0, which give me the domain and codomain of each morphism. Say from X to Y, it'll just give me the object X and the object Y. I've got an identity morphism in E, which says for each object, each element of C0, say I get an arrow in C1, which is identity, and I've got this composition map from the pullback where I've got two morphisms, and they agree the second one having a domain equal to the codomain of the first one. That's this pullback object here. Then I can, of course, compose them. And these various maps have to satisfy some axioms, which I haven't written out here. They're the kind of standard associativity and unitality ones for composition. Now, as a kind of example of these various categories, we might think of E as being the category of like large sets, and C to be internal in that the category of finite sets. So the object of objects is going to be the set of all finite sets, and the object of morphisms, I think, is still a large set. Maybe, I don't know. I'm sure there's some universe in which the sizes are okay, will be the object of morphisms between all finite sets. And as I said, I think I want this general machinery because I want it ultimately to have an analog of this thing for a sort of an analog of the categorical story in this kind of language. Okay, so now we can introduce my construction, which I call prox. So it's going to have the same form as this kind of vibrational power that I sort of sketched earlier. So it's going to be an index category of this nature from E into cat, which is just the sort of general category of categories. I guess small categories. So for some object P in E, this is going to be, again, our object of parameters. I'm going to define a category prox of P. Its objects are going to be the arrows, the generalized elements with domain P. So they're kind of going to be the sort of P-shaped generalized elements of this object, of C object, C0. Then the morphisms from some X, from P to C0, and to some Y, are going to be these, again, these P generalized elements of C1. So we've got some F from P to C1, such that they have the right domain and codomain for each point of P. So that's what these two axioms say. And then we do the same kind of thing for composition. So we copy the parameter, and then we do, I've got these the wrong way around, it doesn't really matter. Then we do F and then G, one consuming one copy of the parameter and the other consuming the other copy of the parameter. And of course, by supposition, these things agree on the intermediate object, and so we can compose them. And for each parameter, because we get an object, and because we have this identity map, it gives us the identity map. And so this thing, which is just this composite, is going to be our identity map. And it's quite easy to show that, assuming C is an internal category, that this is a category because it satisfies those associativity and unitality axioms. And indeed, this is, again, actually an index category. It's functorial. It works the same way by reparameterizing, by pulling back, by precomposing along this map phi. But the crucial extra detail is that we have these like extra objects because they are sort of, parameterized. So we can do things like talk about what the say limits are of parameterized maps. So okay, I've got a page here where I can talk about what some of these might be, and I guess I've got just enough time to do some. I guess maybe I'll do equalizers since I mentioned them earlier. So suppose we've got some F, which is P to C1, and it's really of the type X to Y, where X is P to C0, and so is Y. And so we've got G as well of this type. So that's G and F. So these are two parallel maps, and we might think about, we might ask what's the equalizer of F and G. So that's G. And of course, this should be something like this, X, making this kind of diagram commute, F, G, Y. So, okay, what does it mean for this? This is the inclusion. So what does it mean for E to be this type? Well, okay, first of all, we need to define this object. So each F, G is going to be a map from P to C0. And say we're in this kind of set-like situation I mentioned earlier. It takes a parameter P, and it gives me the equalizer object because we assume that C0 has equalizers. So this is actually an object, and so this is the equalizer of the map F of P and G of P. Cool, that's an object. So I think this is an object. That's fine. All I required was this be a generalized element, which it is. That's nice. So then what's this E? So E is going to be something like P to C1, and it takes P, and it gives me this EP map from eq F, P to G and GP into X, P. And it's easy to see that this is a well-defined thing because it has the right domain and codomain. So that's nice. And then we could, it's not hard to check that this thing actually also satisfies, assuming, this is the universal map given by the equalizer structure in C, that this thing, this E and this parameterized equalizer also have all that nice kind of universal structure. And so this thing is actually an equalizer. And so this is like the first hint that this category really has enough objects. Each of these fibers has enough objects to kind of recapitulate the structure that I had in C. And really, it goes all the way. So we can do this for exponentials. We can do this for the terminal objects. We can do this for sub-objects. We can do this for products. And so in particular, if C is a topos, and so is each prox P, which is nice. I mean, the kind of story goes the same way in each case, right? It goes by saying, okay, well, I've got these generalized objects, these generalized elements, and they pick out the corresponding universal object in C for each choice of parameter, and then the kind of universal maps in each case are going to be the generalized elements which pick out the corresponding universal maps in C. And so the story is the same in each case. So, I mean, I hope that by sketching it for equalizers, that you kind of get the idea for the other bits of the structure as well. So that's quite nice. So this is kind of starting to get towards the kind of thing that I wanted. Of course, we don't have the randomness, and we don't have sort of various parameters. In particular, we don't have this thing where we've got different parameters, P and Q, on the morphisms. And so that's a thing that I think we want to see, and I guess we'll come on to that. Now, in particular, I want to do a version of this story for something called bipara, where both the domain and the codomain of the morphisms might be thought of as being parameterized. Of course, para is the case where we have a kind of trivial parameter on the codomain, and copara is the case where we have a trivial parameter on the domain. And so how do we do this? Well, the way we do this is by extending this prox construction to an index double category over the span, over the double category of spans in E. And if we take E again to be sets, then of course this is well defined because sets has pullbacks, and so we can form this double category. And for each span, if it's like, say something like lambda P Q, we're going to think of the left leg as giving us the parameter on the domain object of each morphism, and the right leg is giving us the parameter on the codomain of each morphism, and the apex of the span is giving us the parameter on the morphism itself. And we're going to have some axioms to say, to give us like conditions under which this whole thing makes sense. And then if we've got spans, then we might also think about decorated spans. In particular, we might decorate the apexes of the spans by, say, probability distributions. And then by taking this kind of decorated span construction, doing the same kind of prox construction over it, we can sort of attach randomness to each of the parameters while holding on to all of the nice structure. At least in each fiber, it gets a little bit messier when we think about the sort of general double categorical structure we get. I haven't really thought through all the double limits that we might have. But at least for now, this is kind of suggesting possible semantics that would be suitable for the kind of notions of random type and random term that I mentioned earlier. Okay, but to get onto this, we need to say what these double categories of decorated spans are. In particular, we need to know what the decorated category of sort of id-decorated spans, which just span is. I'm going to concentrate mostly on this id case just for sort of the purpose of intuition. But I think it's useful to have the kind of general decorated setting in mind. Okay, so what is this double category? Well, let's suppose we've got some lax monoidal presheaf thing F like this. Okay, so then we're gonna build a double category. It's going to have objects. The objects are going to be the objects of E. The vertical one cells are just going to be morphisms in E. So those are these things that go vertically like this. And then the horizontal one cells, okay, and these compose obviously as in E. And then the horizontal one cells are spans in E. So these are pairs of maps like this, F0, F1, equipped in the sort of decorated case with decorations, where we've attached decorations to the apex like this. So this is going to be some alpha, which is an element of F lambda. So this is a set.
Just to be clear, Toby, your monoidal structure on E doesn't have to be product, does it, or is it?
Oh no, but because I said I was kind of working with a E which is set-like. For now, I'm going to assume it is, but I'm pretty sure. I mean,
But what you're
for
saying
most of what I've said,
okay.
it doesn't require it. No. I will highlight the cases where it does have to be a product, certainly. Okay, and the two cells are just going to be these kinds of commuting diagrams. So I've got a morphism on the apexes of the spans, and it has to satisfy this condition that if I use the to sort of pull back from the decoration of on the kind of codomain, it's lambda prime, back to the decoration on the domain on lambda, then these things are equal. And we can check that this, okay, oh, I haven't mentioned horizontal composition. I was going to say this gives us a double category. I promise it does, but let's see what horizontal composition is like. Okay, so first of all, we need to do the horizontal compositions along the spans. So that works by pullback. As I mentioned, I'm assuming that we've got pullbacks in E. So, okay, we can just pull back the sort of codomain and the domain maps to get an apex, which is this pullback object. And so this is nice. This gives us a span by this composition by projecting out onto each leg. On the decorations, it's a little bit more complicated. Say alpha is the decoration for F over lambda, and beta is the decoration for G over eta. Then the decoration is given by this complicated looking thing, F of iota of of L alpha beta. So L is going to be the laxator. So in the case of the probability distributions that I've been talking about, this is just the kind of commutativity of the distribution monad, at least its functor, with the product structure on E. And this iota is just the inclusion of this pullback into the product. And this is just
you're using it there.
Sorry.
Right? You must.
Yeah. I'm using it. It has to be. Yeah. You're right. You're right. Yes. Do I need it? Okay. Yes. I need it here. Yeah. You're right. I need at least this kind of thing. I've got some thoughts, but I want to make progress. Okay. So let's talk about building this double category of proxies over spans. We're going to begin without decorations to keep things a bit simpler. This is going to be an indexed double category. So this is like a double functor from the vertical opposite of span into the double category of categories, functors, and horizontally profunctors. So on objects, prox. So this is, say I've got some object omega. I'm going to define prox of omega to be the same prox of omega as before. Now this is the category where the fiber is this category of sort of proxied objects and morphisms. The vertical one cells are, again, it's going to be the same kind of thing. It's going to be this pre-composition, this pullback idea. Now, so the kind of bit of the structure we're missing so far is what happens on the horizontal one cells. Well, I need to give you a profunctor. So given a span like this from omega to gamma, I need a profunctor from prox omega op and prox gamma into set. So on the objects, say I've got some object A, which is parameterized by omega, and some object B parameterized by gamma, then I can define this set of lambda proxied morphisms. And I have to, again, have a kind of compatibility rule to say that the domains and codomains are what I expect. And so this just says that if I take lambda and I look at the domain, it's really the same thing that I would get by going from lambda using F0 to omega, and then from omega down to D0 using A. And so I have two squares like this. C0 and 2 gamma C1 C0. This is A, this is B, and this is F 1, and this is F0, and this is F, and this is F, and this is Dom, and this is Cod. And so I say that both these squares have to commute. Now, I haven't written it out, but on the arrows, so in prox omega and on the left and on the right in prox of gamma, this acts by internal precomposition. So I want this to be like a profunctor. I want it to be like the Hom functor. So it's kind of like pulling back on the left and it's pushing forward on the right. And really this just works by saying, okay, well, given some C1, I can I get another map. I don't know, omega prime, something like this on the left or on, no, sorry. I don't want to, I guess I can get into this if somebody has a question about it, but I'm conscious of the time. And we get a double category then by taking a double Griffin deconstruction, which I learned about from David Jarvis-Meyer's work on open dynamical systems. Okay, and so how does this go? The objects are going to be pairs of omega and A, which is a sort of omega proxied object, which I write like this. The vertical one cells are just going to be as in the Griffin deconstruction, so they're going to be pairs of map omega to omega prime and a map over it in prox omega from sort of A, which is this object parameterized by omega, to the pullback of A prime, which of course is an omega prime proxied object, pulling that back into prox omega using this prox functor. So it's the same thing that happens in the vertical, the action on the vertical morphisms. And then the horizontal one cells are going to be pairs where I've got a span and an element of the profunctor over that span. And of course, because this is an element of the profunctor over the span, I have to satisfy these sort of compatibility rules. And so this is really, it's a kind of proxied morphism such that it agrees with the domain and codomain objects, which may also be parameterized. And then the two cells are diagrams like this. So this is just the span, so two cells in the span double category, but I have to be able to sort of pull back my, say I've got some F, got my F prime here, and I've got my F here. So the triangle like this has to commute too. So this is a double category, and it is, in my view, it's the kind of double category which is a bit like a kind of proxy version of this bipara category that I described earlier. Okay, so what's the composition like? Vertical composition is the usual Grothendieck thing where I sort of have to pull back in stages. And the horizontal composition is this horizontal composition in spans, and then along with a kind of composition rule of these proxies. So given this kind of a map F, which is, this is like F lambda to C1, so that's from A to B, and this G, which is eta to C1, and that's from B to C, these being parameterized over omega, lambda, and delta, then I can form their composite by taking the parameter to be this apex object, this pullback, and looking at then sort of giving myself morphisms using the kind of FG maps up here, and then composing them in C. And this gives me a map GF from A omega to C delta. And so this is how the horizontal composition works. And this is really a bit more like what happens in, say, in para. And then the two cells compose as in span. So we're just sort of pasting the diagrams there. Okay, so how does it work with randomness? For reasons of time, I'm only going to go over this briefly. But the way this works is we take this pre-sheaf, which on each object, which, as I mentioned, I'm thinking of as sets, and they take the finite support subdistributions on on that object. This is like a kind of noise space, and I'm going to be very generous and allow these to be taking values possibly all the way up to infinity. On the morphisms in E, this isn't going to be the same as the monad structure. This obviously, which is E to E. This has to be E op to set. And so the way this works is by pulling back. So say we've got some omega prime to omega, and of course I can get myself by precomposition a subdistribution on omega prime. I mean, I'm being very generous with the term distribution here because I really want this to be well defined. Then I need to extend the structure of this proxy double category to account for this extra data. So I can define the fibers by taking the objects to be these proxied objects equipped with distributions, say these or subdistributions on the parameter object. The arrows are going to be these proxied arrows just as before. On vertical one cells, it works by precomposition, again, just as for proxies. And then on the horizontal one cells, I have the same idea of giving a profunctor, but I need to account for this subdistribution data. And to make this work, or at least to be able to get the kind of structures I want from the kind of double Grothendieck deconstruction version of this thing, I need to make these things. If I push forward the noise on the apex, the randomness on the apex, I need it to be below, in some sense, the randomness on the objects. Otherwise, I kind of don't know what to do with this randomness. So this, to make this a little bit more precise, I can define a poset structure on these sets by saying a kind of distribution is below another one if it is, when I restrict it to the support of, when I restrict alpha here to the support of alpha prime, then they end up being the same subdistribution. And on two cells, this is again the same thing as before. It's just this this kind of diagram with this compatibility condition. Okay, so that's this thing I called stock prox. I'm going to claim that it will do enough of what I want. There are a few details yet to be just described or particularly written down. But first of all, I'll go back to prox without the randomness. So by quotienting out the two cells, right, I wanted one category because it's just easier for me to think about right now. So if I quotient out the two cells, I get a one category, which has almost all of the nice structure. I think at least if you do the quotienting right, you get all of the nice structure, but the quotienting gets a bit ugly, that I had in C. I think it would be a bit nicer to talk about double limits, but I haven't got around to it yet. But at least it looks promising that up to two cells, up to a sort of reparameterization, I can still talk about, say, equalizers of these kind of doubly parameterized maps. The same kinds of results hold for this stock prox construction, as long as I quotient away the connected components in F. That is to say, if I've got a way of going from one distribution to another according to the two-cell structure that I've quotiented away, then I can consider those distributions to be equivalent as well. Again, that's a bit ugly, and so I kind of need a better way of doing that. But at least for now, this is kind of pointing towards answers for the motivating questions that I started with. And the kind of task, apart from to look at these kind of things like the double limits, is to really start playing around with what it means to have something like a random term or a stochastic type in this kind of way. I did leave some space at the end here to do some calculations. And indeed, I also left some space to talk about, given a notion of proxied morphism, or rather defining a notion of generative model using these proxied morphisms, what it might mean to define a Bayesian dependent optic. In principle, if I have some parameterized section of some bundle, I can think of this, as I mentioned, as a kind of generative model. And this thing I can think of as, say, a kind of parameterized or randomly parameterized B-dependent type. But I am aware of the time, and so I guess we'll have to come to that another time. But the thing I'd like to say is that it does look to be the case that this fits into the story that's being begun to be told about fiber optics. So in the recent preprint from Strathclyde on this, where we can think of dependent optic, or at least a fiber optic, as being, say, the pullback of two vibrations, where one of them is given, where both of them are kind of given by actions of some bicategory on a category. Here, I take the bicategory to be spans, and this category to be the kind of category I get after this quotienting. And this does seem to give me some notion of fiber optic, which I can make, compose, and behave like Bayesian lenses do. And in fact, I have a notion of a kind of notion of Bayes rule for this setting as well, which is quite nice. And so this is all looking promising. I guess this is kind of a research talk, and I'm sorry about the technical problems, but I hope you got an idea of the things I was trying to get to or get towards. I'd love to talk about all of this stuff whenever might be sensible. And if there's time for questions, maybe that will be now. Thank you.
Okay, thanks, Toby. So thanks for the talk. Do we have questions?
I do have one question, if it's possible.
Yeah, please.
Yeah. So Toby, there was a slide in your talk, I think quite at the beginning. It's called structuring proxy, where you actually like compute the equalizer in. Well, I don't really understand where proxy. Could you go over that again? Because I don't understand where the equalizer gets computed.
Oh, well, I'm just assuming. So I'm assuming that there are equalizers in C, right? So for each P in P, I get a map FP from XP to YP, and a map GP from XP to YP. And I can ask, what is the equalizer of FP GP for each P?
But wait, so you're working internally in E.
I mean, so I'm assuming C has limits, equalize.
C is going to be typically a Markov category, right? A category of Markov kernels. Typically.
No, here it's assuming it's just a category with equalizers.
Okay.
So it has equalizers internally.
Yes. So C isn't like a Markov category.
You're fixing a P, right? Which is the
C is like finite sets or something.
Right.
So I've got a finite set. I've got finite sets XP and YP. And this is FP, GP. And so I've got this, I'll write this as EP as the inclusion. And so I've got this equalizer for each P. And so this gives me a generalized element of C0, which takes P to E, F, P, G, P. And I get a generalized element of C1, which takes P to this map, EP. And I can show that this structure is an equalizer, or gives me an equalizer in props P. In particular, I can show that if I've got some UP to XE that factors that makes this diagram commute, then it must factor through this equalizer object accordingly. And the reason that holds is because it holds in C. And so I would say that the Markov, I'm not assuming any Markov structure on C because I want to kind of externalize the randomness. I want to go to this setting that people often use in kind of scientific papers where they have this kind of randomness from some other source. And there they have deterministic maps and some other randomness, which comes from somewhere else. It comes from this like ambient universe. And so that's why I really only care that C is like a category of deterministic maps. It doesn't need to be a category of stochastic maps because I'm kind of aiming to add the randomness in from this external universe.
Great. Maybe we have time for one more quick question before we stop the live stream.
We have a raised hand.
Arthur?
Hi. Thanks for the talk. I don't know if this is short though, but it's just a motivation/conceptual question. So if you have a Markov category, I can make sense of what it means to do Bayesian updating. And if I had stochastic maps, I can, write down the definition. Is part of the reason for introducing para of, maybe this Markov category to have a little bit more control about what kinds of morphisms we are trying to compute, like with respect to Bayesian updating. But, if I understood your talk, you're saying that, it doesn't have a lot of nice categorical features. So we try to maybe add on those categorical features by a new construction that sort of takes the best of both worlds. It gives you some nice computational aspects, but it also gives you some nice categorical features. Is this kind of what the whole point of your talk was?
Yes, that's exactly the point of my talk. I want to be able to kind of talk about these generative models or like these maps, like just these maps X to sort of dy, particularly the ones that have this kind of structure where I've got some alpha, whatever it is. I want to be able to talk about these things as if they were, or maybe as stochastic terms. I want to say, here, this thing really is a term in some context that is like this thing, and that a section of this bundle. Because often it seems to be the case that people who are doing modeling in situations where there is randomness, they want dependent types, or they kind of talk about things as if they had dependent structure, but it's kind of missing. And yes, so I want to be able to have this kind of best of both worlds, this kind of a setting where I can sort of do both, basically. Yeah.
I see. Thank you.
Okay, well, I think there may be other questions, but let's just stop the recording, thank Toby again, and then resume with informal time. Thanks again, Toby.
Thanks, everybody.